Which of the following statements best describes sklearn label propagation's primary use case? A. Classifying data with a small amount of labeled data and a large amount of unlabeled data. B. Clustering data with a predetermined number of clusters. C. Predicting continuous target variables based on labeled data. D. All of the above. Correct. Label propagation is indeed a powerful tool for classifying data when you have a limited number of labeled examples and a large set of unlabeled data. It propagates labels from the known data to the unlabeled data based on their similarity, allowing it to effectively classify the unlabeled data. Correct. Label propagation can be used for clustering by assigning labels to unlabeled data based on their similarity to labeled data points. It automatically discovers natural clusters in data, making it a valuable tool for unsupervised learning. Correct. While not as common as classification and clustering, label propagation can be adapted for regression problems where the target variable is continuous. It can estimate target values for unlabeled data based on labeled examples. Correct. As seen in the explanations above, label propagation can handle classification, clustering, and regression tasks, making all of the above the most accurate description of its primary use case. D. All of the above. A machine learning paradigm where the model is trained on both labeled and unlabeled data. It leverages the unlabeled data to improve performance. Imagine you have a large dataset of customer reviews, but only a small portion are labeled with sentiment positive, negative, neutral. Semi-supervised learning techniques like label propagation can help you classify the remaining reviews based on the labeled data and their similarity to each other. You have a dataset of 1000 customer reviews, but only 100 are labeled with their sentiment. Using a semi-supervised approach, you can train a model on the 100 labeled reviews and use it to infer the sentiment of the remaining 900 unlabeled reviews. A semi-supervised learning algorithm that propagates labels from labeled data to unlabeled data based on their similarity. You have a large dataset of images, but only a small subset is labeled with categories, e.g., cats, dogs, birds. Label propagation can efficiently classify the remaining images by propagating labels from known data to the unlabeled images based on visual similarities. Implementation of label propagation in sklearn. Providing a convenient way to use this algorithm. If you are working with Python and sklearn, you can easily implement label propagation for various tasks using the sklearn semi-supervised label propagation class, used to determine the similarity between data points, which is crucial for label propagation. In the image classification example above, a nearest neighbors algorithm could be used to determine the similarity between images based on their pixel values. Images that are visually similar would be considered closer neighbors. What technique can be used to efficiently propagate labels from a small set of labeled data to a large unlabeled dataset in a semi-supervised learning scenario, effectively leveraging the inherent structure of the data and the relationships between data points? A. K-means clustering. B. Principal component analysis (PCA). C. Label spreading. D. All of the above. A. K-means clustering. K-means clustering is an unsupervised learning algorithm used for grouping data points into clusters based on their similarity. It does not utilize labeled data for propagation, making it unsuitable for semi-supervised learning. False. B. Principal component analysis (PCA). Principal component analysis (PCA) is a dimensionality reduction technique that identifies the Principal components of a dataset. Representing the directions of maximum variance. While it can be used for data preprocessing in semi-supervised learning, it doesn't directly propagate labels. False. C. Label spreading. Label spreading is a semi-supervised learning technique that uses a graph-based approach to propagate labels from a small set of labeled data to a large unlabeled dataset. It leverages the inherent structure of the data to effectively infer the labels of unlabeled instances. It works by constructing a graph where nodes represent data points and edges represent the similarity between them. The algorithm then iteratively propagates labels from labeled nodes to their neighbors, considering their similarity in the existing label distribution. This technique is particularly effective in scenarios where there is a significant amount of unlabeled data and limited labeled data. By leveraging the underlying structure of the data, label spreading can significantly improve the accuracy of classification and clustering tasks. Label spreading is a powerful tool in semi-supervised learning, particularly in situations where obtaining labeled data is expensive or time-consuming. By exploiting the intrinsic relationships between data points, it can enhance the performance of various learning algorithms. True. D. All of the above. As explained above, K-means clustering and PCA are not primarily used for propagating labels in semi-supervised learning, while label spreading is a suitable technique. The statement all of the above is incorrect. False. Correct answer. The correct answer is C. Label spreading, as it aligns with the question's description of propagating labels effectively in a semi-supervised setting. True. C. Label spreading. Semi-supervised learning. Semi-supervised learning is a machine learning paradigm where the model is trained on a dataset containing both labeled and unlabeled data. It aims to leverage the information from the labeled data to infer labels for the unlabeled data. This approach is valuable when obtaining labeled data is expensive or time-consuming, while unlabeled data is abundant. For example, imagine you want to train a model to classify images of cats and dogs. You might have a small set of labeled images, where each image is manually annotated as cat or dog. However, you might also have a massive collection of unlabeled images. Semi-supervised learning allows you to use both the labeled and unlabeled data to improve a model's performance. Image classification: training a model to identify different objects in images using a small set of labeled images and a large dataset of unlabeled images. Text categorization: classifying text documents into different categories using a limited set of labeled documents and a large corpus of unlabeled text. Label propagation. Label propagation is a general term referring to methods that propagate labels from labeled data to unlabeled data. These methods typically exploit the underlying relationships or similarities between data points to infer the labels of unlabeled instances. Label spreading is a specific instance of label propagation that utilizes a graph-based approach. Social media analysis: identifying the sentiment positive, negative, neutral of social media posts by propagating sentiment labels from a small set of labeled posts to a larger set of unlabeled posts. Customer segmentation: classifying customers into different segments based on their purchasing behavior using a limited set of labeled customer data and a larger dataset of unlabeled customer information. Graph-based learning. Graph-based learning is a machine learning approach that represents data as a graph, where nodes represent data points and edges represent the relationships between them. The graph structure can be used to infer information about unlabeled data points by considering their connections to labeled data points. Label spreading is a prime example of graph-based learning in semi-supervised scenarios. Fraud detection: detecting fraudulent transactions by building a graph of transactions and propagating labels of known fraudulent transactions to other suspicious transactions. Medical diagnosis: diagnosing diseases by constructing a graph of patient symptoms and propagating labels of known disease symptoms to other patients exhibiting similar symptoms. Similarity measures: similarity measures are used to quantify the degree of resemblance between data points. In graph-based learning, these measures determine the weights of edges connecting nodes, indicating the strength of their relationship. Common similarity measures include Euclidean distance, cosine similarity, and Pearson correlation. Image classification: using similarity measures to determine the degree of resemblance between different images based on their features. Text categorization: measuring the similarity between different text documents based on their vocabulary and word frequencies. Iterative propagation: iterative propagation is a core concept in label propagation methods. It involves repeatedly updating the labels of unlabeled data points based on the labels of their neighbors and their similarity relationships. The process continues until the labels converge or a specified number of iterations is reached. Recommendation systems: recommending products or services to users by iteratively propagating the preferences of similar users based on their interactions with the system. Natural language processing: inferring the meaning of words or phrases in a text by iteratively propagating labels from known words to unknown words based on their context and co-occurrence patterns. Label smoothing: label smoothing is a technique used to prevent overfitting in semi-supervised learning. It involves slightly smoothing the labels of labeled data points by distributing some probability mass to other classes. This helps the model generalize better to unseen data and reduces the risk of making overly confident predictions. Image classification: smoothing the labels of training images to prevent the model from becoming overly confident in the assigned labels. Improving generalization. Text categorization: applying label smoothing to labeled text documents to make the model less susceptible to overfitting on specific training examples. Confidence scores. Confidence scores represent the model's degree of certainty in the assigned labels. In label propagation, confidence scores are often calculated for unlabeled data points based on the labels of their neighbors and the strength of their connections. These scores provide insights into the reliability of the propagated labels. Fraud detection: assigning confidence scores to transactions based on their similarity to known fraudulent transactions, enabling the model to prioritize high-risk transactions. Medical diagnosis: providing confidence scores for potential diagnosis based on patient symptoms and their relationship to known disease patterns. Unlabeled data. Unlabeled data refers to data points that do not have associated labels or ground truth information. In semi-supervised learning, unlabeled data is used alongside labeled data to improve the model's performance and generalization ability. Image classification: using a vast collection of unlabeled images to augment the training data and improve the model's understanding of visual patterns. Text categorization: leveraging a large corpus of unlabeled text to help the model learn more about the language and relationships between words and categories. Labeled data. Labeled data consist of data points that have associated labels or ground truth information. In semi-supervised learning, labeled data is used to guide the model's learning process and provide initial guidance for inferring labels for unlabeled data. Image classification: using a small set of manually annotated images as labeled data to provide Initial information about the classes to the model. Text categorization, employing a limited set of labeled documents to provide the model with examples of different text categories. Image classification. Image classification is a computer vision task that involves assigning labels to images based on their content. This task can be significantly enhanced by semi-supervised learning, using unlabeled images to improve the model's ability to recognize patterns and distinguish between different classes. Medical image analysis, classifying medical images, e.g., X-rays, CT scans to diagnose diseases or identify abnormalities. Autonomous driving, classifying objects in images captured by self-driving cars to enable safe navigation. Text categorization. Text categorization is a natural language processing task that involves classifying text documents into different categories based on their content. Semi-supervised learning can be applied to text categorization to leverage a large corpus of unlabeled text to improve the model's ability to discern different categories. Email spam filtering, classifying emails as spam or not spam using a small set of labeled emails and a large corpus of unlabeled emails. News article classification, categorizing news articles into different topics, e.g., politics, sports, entertainment based on their content. Social media analysis. Social media analysis involves extracting insights and understanding from social media data. Semi-supervised learning can be used to propagate labels, e.g., sentiment, topic, from a small set of labeled posts to a larger set of unlabeled posts. Brand monitoring, analyzing customer sentiment towards a particular brand based on social media posts. Trend identification, identifying emerging trends and topics in social media by propagating labels from known trends to new posts. Customer segmentation. Customer segmentation is the process of dividing customers into different groups based on their characteristics and behaviors. Semi-supervised learning can be used to propagate labels representing customer segments from a small set of labeled customer data to a larger dataset. Targeted marketing, identifying customer segments for targeted marketing campaigns based on their purchasing behavior and preferences. Customer service optimization, providing different levels of customer service based on customer segments and their needs. Fraud detection. Fraud detection involves identifying fraudulent activities or transactions. Semi-supervised learning can be applied to fraud detection by propagating labels of known fraudulent activities to other suspicious activities. Credit card fraud, detecting fraudulent credit card transactions by propagating labels from known fraudulent transactions to other suspicious transactions. Insurance fraud, identifying fraudulent insurance claims by using semi-supervised learning to propagate labels of known fraudulent claims to other suspicious claims. Medical diagnosis. Medical diagnosis involves identifying and classifying diseases based on patient symptoms and other medical information. Semi-supervised learning can be used to propagate labels of known disease symptoms to other patients exhibiting similar symptoms. Disease prediction, predicting the likelihood of a patient developing a specific disease based on their symptoms and medical history. Early diagnosis, identifying early signs of diseases by propagating labels of known disease indicators to other patients. Recommendation systems. Recommendation systems suggest items, e.g., products, movies, articles that a user might be interested in based on their past behavior and preferences. Semi-supervised learning can be used to propagate user preferences from a small set of labeled users to a larger user base. E-commerce recommendations recommending products to customers based on their past purchases and browsing history. Music streaming recommendations suggesting songs or albums to users based on their listening habits and preferences. Natural language processing. Natural language processing (NLP) involves the interaction between computers and human language. Semi-supervised learning can be used in NLP tasks to propagate labels, e.g. sentiment. Topic: from a small set of labeled text to a larger corpus of unlabeled text. Sentiment analysis determining the sentiment positive, negative, neutral of text based on a small set of labeled text and a larger corpus of unlabeled text. Text summarization summarizing large amounts of text by propagating labels of important topics or concepts to other parts of the text. What is the primary function of scikit-learn's semi-supervised self-training classifier? A. It learns from labeled and unlabeled data simultaneously, utilizing labeled data to guide the learning process of unlabeled data. B. It exclusively trains on unlabeled data, attempting to discover underlying patterns and structures. C. It primarily works with labeled data, but it can leverage unlabeled data for improved performance if available. D. All of the above. True. This is a key aspect of self-training. The classifier learns from the labeled data, and then uses this knowledge to predict the labels of unlabeled data, which is then used to further refine the model. True. This is a part of the process. The algorithm uses the labeled data to guide the training process of unlabeled data, effectively discovering patterns and structures within the unlabeled dataset. True. This is a common strategy in semi-supervised learning. The classifier uses labeled data as its primary source of information but can enhance its performance by incorporating unlabeled data. True. The self-training classifier is a versatile algorithm that can work with both labeled and unlabeled data, effectively combining the advantages of both. It utilizes labeled data to guide the learning process and simultaneously tries to uncover patterns within unlabeled data, resulting in improved performance. D. All of the above. A type of machine learning where the model is trained on a dataset that includes both labeled and unlabeled data. It aims to learn from the labeled data and then use this knowledge to label the unlabeled data. Image classification with limited labeled data. Text categorization with abundant unlabeled text. Customer sentiment analysis. Fraud detection. A semi-supervised learning technique where the model first learns from labeled data and then uses its knowledge to predict labels for unlabeled data. The model then uses the predicted labels to further train itself, iteratively improving its accuracy. Data that has been manually annotated with labels, such as classifications or tags. This data provides the model with explicit examples of the relationships between features and labels. Training a spam filter labeled data would consist of emails that have been classified as spam or not spam. Suppose you have a dataset of customer transactions with labels indicating whether each transaction was fraudulent or not. This labeled data can be used to train a model to identify fraudulent transactions in future. Data that has not been manually annotated with labels. This data can provide valuable insights into the underlying patterns and structures within the data. But the model needs to learn how to interpret it. From sklearn, semi-supervised import self-training classifier. From sklearn, linear model import logistic regression. From sklearn, datasets import make classification. X, Y make classification n samples 1000. N features 20. N informative 10. N redundant 5. Random state 42. Splitting into labeled and unlabeled data. Example 20 labeled, 80 unlabeled, X labeled X200, Y labeled Y200, Z unlabeled X200. Classifier self-training classifier logistic regression. Unlabeled data's unlabeled. Classifier, fit X labeled, Y labeled, YPRED classifier, predict X unlabeled. Evaluate the model. This code demonstrates how to use the self-training classifier in sklearn. It first generates a synthetic dataset using make classification and then splits it into labeled and unlabeled data. The classifier is then initialized with a base model logistic regression, in this case int a. Unlabeled data is provided. After fitting the model on the labeled data, it can be used to predict labels for the unlabeled data.